Hello and welcome to our final E&M project, using solenoids as magnetic stabilization and control systems. Now here we have an image of a basic solenoid. Now a solenoid is essentially just a helical loop of wire that's been wrapped around n number of times to actually generate a magnetic field when you have a current pumped through it. There are two factors that will essentially dictate how powerful the magnetic field is that a solenoid generates. The first one of those is actually just the number of wire loops that are in the solenoid, how tightly wound the wire is and how large the solenoid is. That's N. And the second is the current, which is I, and then that's just how many amps are passed through the wire. Our goal is to actually use a solenoid to control the position of a neodymium magnet. So first let's talk about the two components of our system, and then we'll get into how the system actually works. First is our solenoid. Same basic principles as what we discussed before, however we are actually assuming that our solenoid is of finite length, which means that we need to use a slightly different equation, but the same basic principles still apply. The other component is our neodymium magnet, which is essentially just a simple spherical magnet which has one hemisphere that has a negative polarization and the opposite hemisphere that has a positive polarization. So we've got these two objects, our magnet and our solenoid, and we want to make a control system out of them. So what can we actually do with them? If we were to set the magnet up next to the solenoid, where the solenoid is unpowered, and we were to secure the solenoid down to a plane but left the magnet free to roll, if we started to tilt the plane up and down, then the magnet would obviously start to roll off. But if we started to increase the current flowing through the solenoid as a function of the angle which the plane is tilting, let's say it's tilting down, then we would actually be able to create an attractive force between the solenoid and the magnet, which could counteract the gravitational force, which is pushing the magnet down the plane. So let's address some of the assumptions that we've made with this system. The first is that the magnet orientation is going to be locked to the axis of the solenoid, which essentially means that if we were to draw a line between the two poles of the magnet, then it would line up directly with the center axis of the solenoid. The second assumption that we made is that we're working in a frictionless environment. The third is that the magnet is going to be moving along the z-axis, which is the center axis of the solenoid. And we've also assumed the magnet is a magnetic dipole. We're also assuming that the solenoid radius is negligible. So the first thing that we need to find is our force equation, the relationship between the sphere and the solenoid and how that creates a mechanical force. And that is given by the gradient of the magnetic moment of the sphere dotted with the magnetic field of the solenoid. So first let's talk about the magnetic field of the solenoid. Now it's given by a modified version of the same equation that we discussed before, except now this new equation has a modifier built into it for the fact that the solenoid is not of infinite length but of a finite length, and that our point of observance is somewhere outside of the solenoid. Now the magnetic moment is a bit trickier to find. We find this by integrating the magnetization of the sphere over the volume of the sphere. And we actually know the magnetization because the magnetization is equal to the residual magnetic field of the sphere over mu naught. Since Br and mu naught are not variables with respect to the volume of the sphere, we can say that the magnetic moment of the sphere is equal to Br over mu naught times the volume of the sphere, or Br over mu naught times 4/3 pi r cubed. So now that we've found the magnetic moment of the sphere and the magnetic field of the solenoid, let's plug those two values into our force equation here. So now that we have our magnetic moment and our magnetic field, we can actually plug those back into our force equation, take the gradient of the dot product of them, and then we can calculate our force. So then, since both of these values are in the z direction, then we can just multiply them together and take the gradient, which we have here. And we know that since this is the force generated by the solenoid on the magnet, we know that it has to counteract the force of gravity. And the force of gravity is given by mg sine theta, where theta is the angle above or below horizontal. Now we can actually isolate the current in our force equation, and this actually will tell us how much current we need to pump into the solenoid for any given angle, and any number of wire loops in our solenoid in order to keep the ball stationary. Thank you all for watching. Our next step is going to be to make a physical system based on the theoretical model that we've laid out here.